Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fakhr Lodi and this is our 28th lecture of Formal Methods for Software Engineering. पिछले कुछ lectures से we have been discussing algebraic specifications. In the last lecture we saw the specification of a relatively speaking complex system which was built by first building or developing specifications for smaller components and then using those components in the specification to build the specification of this more complex filing system. तो फाइलिंग सिस्टम की स्पेसिफिकेशन जो हमने पिछली बार देखी थी उसमें अगर आपको याद हो अगर जब हमने उसको छोटे छोटे कंपोनेंट्स में डिवाइड कर लिया तो आफ्टर दैट द स्पेसिफिकेशन इटसेल्फ वाज नॉट वेरी वेरी डिफिकल्ट. द फंडामेंटल कॉन्सेप्ट इन algebraic specification is that what we do is we define the system in terms of its external behavior. Components as abstract data types. And these abstract data types, they provide interface and with certain properties, and those properties and interfaces could be used in other specifications to build a larger system. So here is a very simple kind of depiction of what we have in the case of algebraic specifications. In order to develop a larger system, we have a subsystem and a second subsystem. We define interfaces for each one of these. Each one of these subsystems is defined in terms of the operations that are supported by it plus what it uses from the other subsystem. So हमारी specification जो है is limited to, our interaction is limited to the interfaces only. When subsystem A uses the services of subsystem B, it only uses the interfaces and it does not care about what is inside this thing. This is what the basic philosophy of object-oriented paradigm is. So what we have here is, we have the entire implementation hidden inside, and the only thing that is externally available is the interface itself. And that interface provides the functionality which has been specified in terms of algebraic specifications. So algebraic specifications say what we do is we specify the interface, we specify the behavior of this entity in terms of the operations that are exposed to the outside world, and then those operations can be used to develop bigger specifications. So from smaller subsystem specifications which are developed independently, we develop the specification of this bigger system. And since this is one of the leading methodology for developing systems, developing complex systems, therefore algebraic specifications can become very useful and handy when we develop systems. क्योंकि हम सिर्फ external interfaces पे बात कर रहे हैं, and what we want to do is we want to specify the behavior of the system in terms of the external interfaces that have been exposed and nothing else, as an abstract data type. So the subsystems, they are specified as abstract data types. So abstraction की वजह से उसको use करना आसान हो जाता है. So this is a very powerful tool that we have at our hands. Algebraic specifications have been the focus of research for the last 30-40 years. And many different languages and tools have been developed based upon the algebraic specifications. Some of the most important tools and the languages that we have, they come under two families, so to speak. The first one is called the large family of specifications, large family of algebraic specifications, and the second one is known as the OBJ family. Both of these families, they have been developed sort of independent of each other. They have different philosophies, but their bases are from algebraic specifications. So they use this algebraic specification, the fundamentals of algebraic specifications, and they build systems and they build specifications according to their own syntax and semantics. We shall first discuss large. What is large? Large is a family of specifications which has a number of tools in it. Essentially, large specifications take a two-tier approach to defining specifications. The first tier is known as large specification language, which is independent of any implementation language. Then we have what is known as the large interface language, and that large interface language is dependent upon the implementation language, and it is very, very closely related to the implementation language. And finally, the implementation uses both these specifications to build the system. So let me show you this hierarchy, what is meant by this, and what are the different components in the large specifications, and then I will talk more about the large specifications. So in large, we have one set of specifications. This is known as the large shared language. This large shared language incorporates all the specifications, which includes imports and sorts and so on and so forth. The specification in large shared language is known as a trait. We shall be talking about those traits also. So this is one tier of specification, large shared language, which is independent of any implementation. Then we have large interface specifications. These interface specifications are written in what is known as large interface language, or LIL. This is LSL, this is LIL. And this part is dependent upon the implementation language. So there are many different interface languages. There are many different LILs. There is a large interface language for C. There is a large interface language for C++. There is a large interface language for Smalltalk, and so on and so forth. So both of these, the whole thing, the interface specification and the traits that we have here, they form what is known as the local specifications. this is the specification part of our system. And then we have the program units. So these program units, they provide the implementation, and they are obviously written in the corresponding programming language for which we have written this interface specification. So this program unit satisfies the interface specifications, which is based upon the traits which have been written in the large shared language. And hence we have actually this part is the specification part, and this is the implementation part, and this is the two-tiered specification approach in large in general. So here what we have seen is, we have seen a level of specification. The approach here is that, we don't just have to write the specifications, we have to actually implement. We have to write the code, we have to build the program also. So what we do here in this case, we write specifications for our abstract data types in what is known as large shared language. This large shared language is independent of any implementation. But then what they say is, okay, what we need to do is, we need to now take it and implement it. And this implementation could be in any of the different programming languages that we have. We could have C, C++, Java, Smalltalk, other languages. So what do we do? Should this shared language, how can we take this shared language? How can we take these specifications written in this shared language and map those specifications onto our programming language? How can we do that? So what they do is, they say there is an intermediate step from the shared language specification to the actual implementation, and that intermediate step is what is known as the interface specifications. Remember, in algebraic specifications, what we are doing is, we are building interfaces. We are specifying interfaces. So this interface specification is based upon the specification that we have done earlier on in shared language. Then this interface specification is written, or it uses a syntax which is closely similar to the syntax of the target implementation language. For example, if we wanted to implement this thing in C++, we would write the interface specifications in C++. Now these interface specifications, they will be, as I mentioned earlier, very closely related with the shared specifications. But the shared specifications, they are more flexible. They are not constrained by any of the implementation issues. So we simply say, okay, this is what we want. We are not going to say how should it be implemented. But as we go to the implementation, obviously there are certain constraints. We cannot do certain things in one programming language, and we may not be able to do certain other things in some other programming language. So there are implementation constraints, and the interface language actually addresses those implementation constraints. So as we move closer to our implementation, we add some more detail, but by adding that detail, we limit our scope. We reduce the scope for flexibility. We are coming closer to implementation, and we are giving one particular solution. And this is what the large interface specification language does. It takes you one step closer to the implementation language, and since the syntax and the semantics, they are very closely associated with the target language in which we actually intend to build the system, what we do is, we can very easily provide an interface between our program and the specifications that we have. So this is all what we are going to do. What I'm going to show you is some basic information about large shared language and the interface language. And then there are other tools available to us. And those tools are what is known as large prover. That large prover actually is used to prove certain properties about these specifications. So it is not just that we build those specifications using algebraic formulations, but we can also argue about these specifications. We shall be looking at those as well. So in general, what do we have? We have the large shared language. We have the large interface languages, which is a set of languages. We have the large provers, which are used to prove certain properties of the traits that we build in the large shared language. And hence, we can show whether a specification is consistent or not consistent and other properties of that. So let me go back onto a slide and show you certain things about large, and then we will continue this discussion. Some aspects of large languages are, number one, composability. It provides incremental construction of specifications from other specifications. Large, like other algebraic specifications that we have seen earlier, it lets us build specifications from smaller specifications, already built specifications. So you can compose specifications that you have already written and use those specifications to build complex systems. So this is one of the attributes or characteristics of large shared language. Then there is this emphasis on presentation. These specifications are readable, and large composition mechanisms are operations on specifications rather than on theories or models. Readability is one of the very important concerns of the large design. The designers wanted the large specifications to be quite readable. So the compositions, once again, they are built on the interfaces that we provide. Okay, they don't go inside the implementation details and talk about it, and hence discuss and use the interfaces at an abstract level, and hence they are more readable. Then it is suitable for integrated interactive tools. It is good for interactive construction and incremental checking of specifications. So we have, tools which are interactive, so you can build the specifications interactively and incrementally keep checking whether you are building the specifications properly and are the specifications consistent or not. So it is not that you have to build the entire specification and then check and use those provers and those kind of things on these specifications. So that also means that you can use these tools on incomplete specifications also. So you don't have to complete the specification to use these tools. This is a very important design parameter. And then there is the semantic checking, which lets checking of specs when they are being constructed, that is theorem prover for semantic checking. So once again, this is what I have already mentioned, that you can use these theorem provers to check the semantics of the specifications. So it is not just the interface part that we are concerned with. We are also concerned with the semantics part, and then we can use tools such as theorem provers to argue about the semantics of the specifications and check whether these specifications are correct or incorrect. So this is also some of the things. Now, there are certain limitations here. I will be talking about those limitations a little later, but even with those limitations, these tools are quite powerful and give us a lot of information and power to build specifications incrementally. Trait is the basic unit of specification in large specification language or large shared language. It introduces operators and specifies their properties, sometimes collections of operators corresponding to an ADT. So the first thing that we have here in the large shared language is the notion of what is called a trait. Trait जो है ये असल में ये बहुत उससे मिलती जुलती है, although it has certain other features also, but more or less this is what we have seen earlier. This is what the algebraic specification is. जो algebraic specifications हैं वो trait की form में लिखी जाएंगी. So we have the operations and we have the axioms on those operations, and this is what we are going to have. So हमने traits ही build करनी है इसमें. Then we have a theory. Theory is a set of theorems that can be proved about the terms defined in a trait. Theory contains equations and inequations that can be proved by substituting equal for equal. But if two terms cannot be proven to be equal, then they are not necessarily unequal. Also, if two terms are not provably unequal, it does not mean they are equal. ये एक important concept है. What we are saying here is, we are saying, there is this notion of theory. This theory is something that is provable. So हम अपने जो large prover जो है या theorem provers जो हैं उनको हम use करेंगे to prove or to argue about certain properties of the specifications by substituting equals for equals. तो ये हम इस तरीके से substitute से करते रहेंगे. लेकिन जिस तरीके से मैं पहले जिक्र कर चुका हूं कि there are certain limitations and those limitations, उसमें और भी बहुत सारी वजूहात हैं, लेकिन एक उसकी वजह ये भी है कि we are incrementally building and checking the specifications. So हमने अगर specification अभी complete नहीं की and we are checking, so we may not be able to prove anything or we may not be able to disprove anything. So if we are not able to prove anything, that does not mean it is incorrect. And if we are not able to disprove anything, that does not mean it is correct. Because ये भी हो सकता है कि अभी specification आपकी incomplete है. So ये एक important component है, important aspect है जो हमें याद रखना होगा. Then we have the signature. Signatures are the domains and ranges of the operators used for sort check. We have already seen signatures. So we provide the domain and the range, the input parameters, the type of the input parameters, and the type of the output parameter. this is exactly what we are defining here, that this operation takes this as input and gives us this as output. So this is basically the same thing as you have seen in other algebraic specifications that we have developed earlier on. Then we have the constraints, which limit the operators by means of equations that relate the terms containing them. The constraints, basically what we are saying is, now we are providing the semantics and we are saying, okay, this is allowed and this is not allowed. So those are our axioms. जो हमने ऊपर ऑपरेशंस डिफाइन किए हैं, उनके सिग्नेचर्स डिफाइन किए हैं, उनके लिए हम कंस्ट्रेंट्स कह रहे हैं कि ये हो सकता है और ये नहीं हो सकता. एंड वंस अगेन दैट इज एग्जैक्टली व्हाट वी सॉ in our algebraic specifications. Large interface language is a localized programming language and there are certain dependencies. Each large interface language encapsulates features needed to write specifications in a particular programming language and incorporates large shared language in a uniform way. So after the large shared language, we have our large interface language. जिस तरीके से मैं पहले भी कह चुका हूँ, large interface language is dependent upon the implementation language, or it is very, very closely related to the implementation language. So actually we have a set of large interface languages available. There are a number of interface languages that are there, including C, C++, Smalltalk, and so on and so forth. There are certain implementations for Java also available. So those are the interface language, and then we write our specifications for the interfaces using the LIL. And those specifications are based upon the specifications that we have already written with the help of large shared language. The third component is the large prover. Large prover, or LP, is an interactive theorem proving system for multi-sorted first order logic. It assists users in finding and correcting flaws in conjectures, and it works efficiently on large problems, but it is not designed to find difficult proofs automatically. Large prover, जिस तरीके से मैं पहले भी कह चुका हूँ, it is the theorem prover that large family has. It is quite efficient, quite useful, but it is not supposed to work with very difficult problems, and provide proofs automatically. So you have to work with it. For simple systems, the proofs can be generated automatically and can be shown that, if something is properly done or not. But for more complex systems, very difficult problems, it is not meant to be done automatically. So ये इसकी एक limitation है. It checks for syntax and the type errors in large shared language specifications, and there are two files of input that are suitable for use with large prover: LP axiomization for an LSL specification and LP proof obligations associated with logical claims made by specifiers about the logical properties of these specifications. Large prover basically checks the syntax and the basic consistency of the specifications. और इसमें दो तरह की इनपुट्स इसमें जा सकती हैं. एक तो लार्ज शेयर्ड लैंग्वेज में जो आपने स्पेसिफिकेशंस लिखी हुई हैं वो, and the second is, if the specifier has given certain, assurances कि ये specification, this is what it will do. So that file where the specifier says or gives an obligation for the specification that this specification is supposed to do this, that goes into the large prover, and then large prover takes it and then verifies whether those claims that have been made by the specifier, they have been fulfilled by these specifications or not. Now let us look at the large shared language in more details. LSL specifications define two kinds of symbols: operators and sorts. Operators stand for total functions from tuples of values to values, and sorts stands for disjoint non-empty sets of values and are used to indicate the domains and ranges of the operators. Operators are our functions, our operations that we can perform, and sort is the type जो इससे पहले हम algebraic specifications में देख चुके हैं. So दो चीजें इसमें हैं. Inside a trait you will see operators and the sorts, and basically it's basically the same thing that we have already seen in our algebraic specifications. As mentioned earlier, the trait is the basic unit of specification in LSL. A trait introduces some operators and specifies some of their properties. Sometimes the trait defines an abstract type. However, it is frequently useful to define a set of properties that does not fully characterize a type. Trait is very very similar to our specification. जो हम इससे पहले जिस तरीके से हम algebraic specification में ऊपर हम देख चुके थे कि name of the specification we give that, trait is something similar to that. Is used to define an abstract data type. But traits can also be used to define something which does not fully qualify as an abstract data type. इसकी भी हम कुछ examples देखेंगे, but mostly traits will be used to specify our abstract data types. So we have traits. Inside the traits we have operators and sorts, and that will form our specifications in the large shared language. Here is an example of a trait that specifies a class of tables that store values in indexed places. So here is our trait. So we write name of the trait, which is table colon trait. So this is, we are declaring that this table is a trait. It includes integer. So this is the same as importing integer in our algebraic specifications that we saw earlier. Introduces. So now we have our signature part. New, which gives us a table. Add, which takes a table and an index and a value and puts that value at that index and gives us the modified table back. This membership function, it takes an index and the table and tells us whether it is present there or not. Lookup takes the table and the index and returns the value at that index. Size takes the table and gives us the size as an integer value of the table. So here we saw something what we have already seen, something very very similar. The only difference may be शायद syntax कहीं पर थोड़ा बहुत आगे पीछे हो गया होगा, लेकिन from a conceptual point of view it is almost exactly the same as what we saw earlier in our algebraic specifications. तो इस signature part में कोई चीज फर्क नहीं है, बिल्कुल उसी तरीके से है. The only thing is that it has a specific syntax because it is a language which is processed by a tool, so it has that syntax and that syntax will be used in our specifications. Now let us look at the axioms part also. Asserts for every I1 colon index, comma v colon value, comma t colon tab. So it is saying that it takes three parameters: the index, the value, and the table. And inside this table, for every I, I is not I is a member new. That is, we are saying here in this particular case that, we have these values present in this table. With the new one, when we say have this new basically means that, we have a new table which does not have any value associated with it. So this is what it is denying, that, for all those, the value is present. I is a member of add P, I1, V is equal to I is equal to I1 or I is a member of T. यहाँ पर ये ज़रा थोड़ी सी सिंटेक्स की कॉम्प्लेक्सिटी की वजह से शायद आपको इसको समझने में थोड़ी सी मुश्किल लग रही हो, लेकिन हम यहाँ पर बिल्कुल वही फॉर्मूलेशन यूज कर रहे हैं जो इससे पहले हम कर चुके हैं. यहाँ पर हम ये कह रहे हैं कि ये जो हमारा ये ट्यूपल जो है, जिसमें हमारा इंडेक्स, वैल्यू एंड टेबल, ये तीन चीजें आ जाती हैं, इस चीज को हम देखें तो किसी एक टेबल को, एंड दिस इज वन इंस्टेंस आई, so an instance I has these three values. So first of all, is it a member of new? The answer is no. New में कुछ नहीं है तो ये ट्यूपल भी नहीं हो सकता. और सेकंड हमने इसका एक्सियम जो दिया है वो बड़ा सिंपल सा है. वंस अगेन बिल्कुल वही फॉर्मूलेशन है कि हम ये कहते हैं कि कंस्ट्रक्टर इस पे अप्लाई कर रहे हैं. जब हम कंस्ट्रक्टर अप्लाई करते हैं तो ये ट्यूपल टेबल के बीच में हमने ऐड किया है, सो वो ऐड का मेथड यूज कर रहे हैं. सो इज आई प्रेजेंट हियर? इट इज प्रेजेंट इफ इट इज इन दिस न्यू ट्यूपल, अदरवाइज it will be present if it is already present in the table in which this new tuple has been added. तो ये हम बड़ी सिंपल सी वही फॉर्मूलेशन है, सिर्फ थोड़ा सा सिंटेक्स इसका डिफरेंट है. Then we have lookup add P, I, V, I1 is equal to, if I is equal to I1 then V, else lookup T, I1. Once again exactly the same formulation कि जब हम कंस्ट्रक्टर अप्लाई करते हैं, लुकअप का फंक्शन अप्लाई करते हैं, तो वी आर लुकिंग फॉर सर्टेन वैल्यू. Is it present there? If it matches with the tuple that we have just added, yes, it is present. Otherwise, it will be present if and only if it was present in the table before this new tuple was added to this table. So once again, exactly the same formulation that we have seen so many times. Size of new is equal to 0. Size of add T, I, V is equal to, if I is a member of T, then size T, else size T plus 1. So in this particular case, we are saying size of new is equal to 0. Obviously, when we have just created this table, new, its size is 0. There is nothing in it. तो इसमें तो कोई ऐसी खास बात नहीं है. The second axiom is interesting. In this axiom, what we are saying here is size after adding this tuple into the table, what happens? We are adding this new index in this table. What we are saying is, if the index is already present in this table, हम index और value का pair ले रहे हैं इस table में, key value pair है, so we can be adding indices and the values, corresponding values. It is kind of a dictionary that we are building. एक लफ्ज़ है, उसके against meanings हैं. सो की वैल्यू पेयर्स हैं, टेबल का मतलब ये है. So if the key is already present in the table, what is happening here? If the key is already present, we are not changing the size of the table. And if the key is not present in the table, then we are adding this one new entry into the table and adding the size by 1. Incrementing the size by 1, adding 1 to the size. So what does that mean? इसका साइड इफेक्ट क्या है, इसकी इंप्लीकेशन क्या है? अगर हम इसकी नई एंट्री नहीं डाल रहे, if the key is already present in the table and we are not adding this new entry into the table, so what does this add function do? We are not changing the size of the table, so key is the same. We are not adding a new entry. So add function, what does it do? In this particular case, it is changing the value by replacing the old value with the new value that has been provided here in this tuple. So the add function does two things. If the key is already present, it changes the value, replaces the old value with the new one. And if the key is not present, then in that particular case, it adds a new entry into the table. Now I ask you this question. We have seen the specification. The other axioms that we have seen. ये एक्सियम्स में ये कहां से ये चीज आ गई कि ये जो ऐड जो है, अगर की इज ऑलरेडी प्रेजेंट, देन इट विल रिप्लेस दैट वैल्यू विद द न्यू वन. क्या हमने इससे पहले जो एक्सियम्स लिखी हैं उसमें ये चीज हमने कही है कि ये मैं खुद से कह रहा हूं? और हाउ कैन आई इंप्लाई दिस थिंग, हाउ कैन आई कंक्लूड इट फ्रॉम दिस स्पेसिफिकेशन? Let us go back and have a look at, once again, the axiom for membership. We say I is a member of add P, I1, V is the same as saying as I is equal to I1 or I is a member of T. So ये एक चीज हो गई कि मैं ये कह रहा हूं कि अगर I is equal to I1, then I am not adding anything. Because, then I say, this is what it is. But how about replacing the value? Let us go back and look at the other axiom for lookup. Lookup says, lookup add T, I, V, I1 is equal to, if I is equal to I1, then V, else lookup T, I1. Once again, this is from where I concluded that the value would be replaced. How do I say that? It is saying that if I is equal to I1, then what I get back is V. Now this V is this new value that I have, passed in the add method. So if I was already present, then the old value must have been replaced by this new value V, otherwise I would not get this value V. And if I is not present, then obviously this is not the value that I'm looking at. I'm looking at if the value was already present in the table before I added this new term into the table. So हमने यहाँ पर देखा कि ये जो specifications जो हमने लिखी हैं for this trait, they are very, very similar to the specifications that we have written previously. The only difference is the syntax. Here we have written the axioms in the similar manner that we used earlier on, but the syntax is slightly different. In this case, हमने लिखा था introduces, which basically gives us the signature part, and asserts, which gives us the axioms part. And we wrote it for all I. That means, these axioms must be fulfilled by all instances of the tuples in this table. लेकिन once again, ये चीज note कीजिए कि we do not have to write redundant specifications. ये जो specification खास तौर पे मैंने आपको यहाँ पर दिखाई, जिसमें I showed you that it also means that if the key is already present, then the old value is replaced by the new value. Otherwise, this key is added, or this tuple is added into this table. I could have written specifications, axioms, which would have stated this thing explicitly, but I did not need to do that because my specifications are otherwise complete. They are consistent with each other. जो सबको मिला के आप पढ़ेंगे, सबको मिला के आप देखेंगे, तो आपको इसकी completeness आपको इसको नजर आ जाएगी. There is no ambiguity here. But if there were any ambiguity, most probably, hopefully, if we were using our large prover, that would have caught that kind of thing. अगर inconsistency कहीं पर हो, अगर ambiguity होगी तो शायद वो इसको catch नहीं कर पाएगा. But anyway, what I was saying was that, this specification language large that we have, it's based upon algebraic specifications that we have seen earlier. उसी पे ये सारा का सारा मॉडल बिल्ड किया हुआ है. The differences are in the syntax. There are certain other differences that probably we shall see when we look into the details. There are certain things, for example, algebraic specifications, they are used for complete abstract data types. Here we can have large specifications for something which is not complete abstract data type, which does not fulfill the definition of abstract data type. So we shall see that also, hopefully. So inshallah, अगले lecture में हम इस गुफ्तगू को जारी रखेंगे. We will continue discussing this large specification languages, and I'll show you more specifications and the other tools that we have. Until that time, Khuda Hafiz or Assalamu Alaikum.